It's a big pleasure to introduce Vladimir Berkovich from Weizmann Institute of Science, and he will tell us about Hodge theory for non-Archimedean analytic spaces.
Thank you. And so I started saying that this talk is about the classical Hodge theory, not p-adic, because usually non-Archimedean is associated with p-adic fields, but we are work with other fields. So let me start from the beginning. And so approximately 55 years ago, Deligne introduced the notion of a mixed Hodge structure, and he provided with this structure integral cohomology of complex algebraic varieties. Separated, everything will be separated, I don't say. And so if X is a scheme of finite type over C, then for any n integer, the integral cohomology group of the analytification, complex analytification of X with coefficients in Z is provided with a mixed Hodge structure. And so I just recall that it has other ingredients. W is a finite increasing filtration on the rational cohomology groups, and F is a finite decreasing filtration on complex cohomology groups, which are related in a certain way. I do not remind the definition. And this correspondence is a functor. So I define the category of mixed Hodge structure over C, let us call, and F stands for finite. This means that these are finitely generated abelian groups. Now, what I'm going to talk about some extension of this theory in a slightly unusual direction, but in fact very natural direction. And so let me first of all reduce the field. So let K be a non-Archimedean field. In fact, one can say that just isomorphic to the field of Laurent power series over C, but I want also to introduce notation, and I do not want to fix this isomorphism. And so non-Archimedean field with non-trivial discrete valuation. I recall that non-Archimedean means that from the triangle axial poles. And so let me introduce also notation I use by K node, standard notation. One denotes the ring of integers, the set of all elements of K, whose value is at most 1. So due to this axiom, it's a subring. It's in fact a local discrete valuation ring. Of course, we assume that K is complete with respect to this valuation, as the word non-Archimedean field assumes. And so the maximal ideal is that of this ring is denoted in such a way. It consists of elements whose norm is strictly less than 1, and the quotient, the ring of integers, but by the maximal idea is denoted in this way, and it is the residue field of this field K. And what is the assumption about our field K is that the ring of integers contains the field of complex numbers. And so the restriction of valuation to C is trivial. And the assumption is that C maps bijectively to the residue field, And in fact, this one can easily see if var phi is a generator of the maximal ideal, then one can associate to it an isomorphism, which takes of the field of Laurent power series onto K, which takes Z to 1 pi. Okay, and so I again have to. So you have such a field K, there is a natural filter from the category of algebraic varieties over C to the category of schemes of finite type over K. So it takes X to Xk. And since K is a non-Archimedean field, there is a functor from the category of schemes to the category of K-analytic space, which takes algebraic variety over K to its non-Archimedean analytification. So it's now I want to complete this diagram. And so I'll explain what is the category of mixed Hodge structures or finite also now is the category of distinguished mixed Hodge structures of finite type over K. I'll explain all this. And so I'll construct a commutative diagram of functors. That means that functor in this direction is canonically isomorphic to the functor in that direction. And in fact, also, I want to complete this part, but unfortunately, I can only do it for a full subcategory of the category of analytic spaces. It states analytic spaces embeddable in a boundaryless space. Now I'll give the definition, but I only want to say that it is a full subcategory of the category of so-called strictly K-analytic spaces. I recall that in the analytic spaces I work with, one allows arbitrary real radii of closed disks, but here only so-called rational, in a certain sense, radii are allowed. And it's precisely, they correspond to rigid analytic spaces. It's easier to say who's convenient. And so it's also full subcategory. But it's then one can complete this diagram, and so one can. I will introduce. Unfortunately, I missed here Q. This means that not integral cohomology, but rational cohomology will be defined. And now I explain that you see a different letter C, and so C stands for linearly compact. And so these objects are linearly compact, not, I give roughly speaking, linearly compact vector spaces over Q. And so let me remind you that linearly compact vector space over a field is a topological vector space, which is topologically one of the equivalent definition topologically isomorphic to a projective limit of finite dimensional discrete vector spaces. And so this notion is was introduced by Lefschetz for considering cohomology of spaces if some space has infinite dimensional cohomology groups. And it is the same reason here, because it's impossible to expect that cohomology of analytic spaces are finite dimensional, so that there are many of them. And so, but I'll give the definition of what it is. And so this functor will take a K-analytic space from this subcategory to, I write, describe all these objects. In fact, now let me explain. First of all, as an object, these objects of this category are variations of mixed Hodge structures of a very specific type on a very natural space, which is so this space. And so it's strange notation, but already. So let us consider the quotient of the maximal ideal of K, maximal ideal of the ring of integers by its square is drawn 0, remove 0. And so it is a space. And in fact, these are mixed variation of mixed code structures on this space. So this space is just very simple. It's principal homogeneous space for C star. So very natural. And in fact, variations, this means that not cohomology groups are considered like here, but local systems. Local systems, these are local systems on this space. Because of that, you see I use calligraphic here. Okay, and so these are local systems of finite dimensional vector spaces. Here, local systems, linearly compact vector spaces. But in fact, many more from I'll formulate precise results. Many more analytic spaces come here to this subcategory, not just algebraic varieties, but many more. Okay, and so but now, what is this notation? Let me be back into the classical situation. And so
what does ds mean? Exponent ds, what does it mean?
What?
The ds, well, maybe I cannot read.
Ds distinguished. It stands for distinguished because there are various types of Hodge structures.
You said that Ottfried and very nicely.
Okay, if you, it just one of the two things that local system endomorphism, some loop over this space, it's like C star, eigenvalues are roots of unity. Just this, which is equivalent to say that, but let me first of all, I'm here. And so let me remind you, what is it? And so it is a filtration on rational cohomology groups, which is constructed using resolution of singularities. Now, what is the origin of this filtration, Hodge filtration? It comes from the RAM cohomology groups, in fact, essentially, if one analyzes the construction. And so, in fact, one can define the RAM cohomology groups of X, our algebraic variety. And one provides, again, using resolution of singularities, one provides this filtration F. If X, first of all, if X is smooth, these are usual the RAM cohomology groups. If in addition X is proper smooth, then it's a usual Hodge filtration. But in general, one should define smartly this group for non-smooth spaces, and also, and there is the RAM isomorphism theorem, which is important here, that this group is isomorphic. There is a canonical isomorphism. And so filtration F on the complex cohomology group comes from filtration F on the RAM cohomology groups. And this is, and so the real ingredients of this construction are, first of all, we have integral cohomology groups here, rational, filtration M, and then we have the RAM cohomology groups, filtration there, and there is something instead of this isomorphism, there is the RAM isomorphism theorem, non-Archimedean, which I will explain, which will add them, and in such a way one gets this variation of it. There is. Okay, and so now I want, but if I want to say that only these groups are defined on the whole category of strictly analytic spaces. but only for embeddable, for the subcategory of embeddable to boundaryless space. And now I'll explain, probably it's better to, one defines also these objects, filtrations, and in fact, the reason is eventually one, because like the initial fact which is used like in Deligne's work, Hodge decomposition for cohomology of proper smooth varieties. And so here also everything is in use. And so the construction, of course, includes this construction for arbitrary X.
Can you push the board up?
I want to leave it. So first, in fact, of course, the first, let me call this fact one. One can construct for any n, no, let's say integer n, functors, a functor from the category of strictly K-analytic spaces to the category I have no notation, and so I write quasi-important local systems of few vector space of linearly compact few vector spaces on that space A star one. Why one is here? But because it's a part of some formal log analytic space, and so I don't want to mention it. But it's very simple space, and so quasi-unipotent now it will be clear. And so X goes to its annotation. It's annotation to such local system. Now, such that now I list some properties, not all. There are many nice properties, but the first one, at least it will give some idea how one constructs this object. So first, if there is an isomorphism from X to the generic fiber of special formal scheme, now I'll remind what is it. Scheme over K naught. So what is special? I remind that locally it is formal spectrum of the following ring. So it's a quotient here, several restricted variables, several formal variables, and factorized by an ideal. So it's a very nice ring which is complete in adic topology, generated by these formal variables and the maximal ideal of K. All ideals are closed, and so they're very Newtonian, and so on. And special, and so if there is an isomorphism between X and this generic fiber, it's not necessarily exist, but then there is such an isomorphism induces the following isomorphism of this local system with the following. Now I will explain. I will explain what is the right-hand side. So first of all, what it is. And so it is a you see its notation. It's a functor which is called nearby cycles. I call vanishing cycles. I do not know why, but it's a object of derived category of abelian groups on the following analytic space, C-analytic space. So it's complex of space of this space. A pi is just projection. And so it is like initial starting point or some the heart of the whole theory. And so that I construct not only for Q, also for Z. This complex, when instead of Q, one uses Z. And so one can construct which complex analytic vanishing sets. 11 years ago, I gave a talk here. And so about I talked like it was a program. But one could write instead of QZ, but I do not know what is the object we obtain. But what is miraculously, the left-hand side does depend on this formal model eventually.
What is this H?
H?
Yeah, no, KS. Later. The next formula.
Yes.
The H.
H stands by CERN notation, complex analytification. It's a closed fiber of formal scheme. It's algebraic variety and it's complex multiplication. Just because non-Archimedean analytification denote in such a way. Okay, it's of course I cannot construct this object as just as the one can construct. Okay, and in such a way, now second property, which is if X I call it confined in a certain set, that is, it is isomorphic to space of the following type, where X is quasi-compact. Special formal scheme. Special formal scheme, but here, and Z is a closed formal subscheme. For example, if it is an analytification of an algebraic variety, and so one can show that even one can take for X formal scheme of finite type, just called. And so then these local systems are finite. Finite means that local systems of finitely dimensional vector spaces. It's important, in particular, if X is compact, X is an analytification of algebraic variety, but many more, even if X is a generic fiber of quasi-compact. What is important here, I do not assume that it's quasi-compact, but if it's quasi-compact. Third property, just for it's curious, we do not need it here, but for any prime, there is a canonical isomorphism and the product of this space with QA, but I place hat here. This means that because it's not finitely dimensional space, it's a projective limit of finite dimensional. So we should take tensor product of all this finitely dimensional and consider projective limit. So it's like is canonically isomorphic to okay, and so the property tells that one gets from this rational homology group all Eliadic homology group. Right-hand side defined by Eliadic. Only I want to explain why I use here calligraphic, what precise meaning. In fact, I didn't tell you so far. It's this space, very nice. There is a local system which on this space one can construct of algebraic closures of the field K, algebraic local system of algebraic closure, like there is a natural construction, and so it's algebraic closures. Okay. And this group, it is also a local system which takes var pi point of that space to periodic cohomology groups of the following space. We lift X to completion of algebraic closure, take periodic cohomology groups, and so one can define periodic cohomology groups. Okay. Now, of course, the second part will be when I define introduce the RAM cohomology groups, there will be comparison with the RAM cohomology groups. But let me only say that if X or algebraic variety of C, we start from algebraic variety over C, then what we get just constant local system associated. It is a constant local system associated with rational cohomology of this algebraic variety. Would be okay.
About the object you get, you say it's a local system of this K1 star.
What?
So those cohomology are local systems.
Local systems, yes.
Or as described in terms of representation of
yes. There is represent R. Now, I did not explain what are the quasi-compact. And so, one more property, it's really essential. Thank you, at least now I see that I missed. There is a canonical isomorphism, which explains why linearly compact spaces, how they arrive. There is a canonical isomorphism of this local system with projective limit of such local finite dimensional local system where V runs through compact, strictly analytic domains. It's I just missed. I had to increase. And so it explains that now quasi-unipotent, what it means. Quasi-unipotent means, and so you see here, in fact, when we come to infinite dimensional objects, there are projective limits of something finite dimensional. And so these local systems are quasi-unipotent in the usual sense. But these are just by definition, so everything is explained. Now, let me come to this, which is like less trivial than in the classical situation.
So what's wrong with Z coefficient?
What?
What's wrong with integer coefficients?
Because I do not know what are projective limits of finite dimensional abelian groups.
Okay.
Of course, ideally, if they satisfy Mittag-Leffler condition, it's possible to work. But otherwise, I just do not know. And so it's easier to leave it. I try to do something, but it's a different kind of problem. And okay. One can construct for any functor. Also, the category of strictly analytic spaces. You see, strictly analytic because we have to use formal schemes, and so this enables to the following category: linearly compact. Linearly compact Now I formulate linearly compact but distinguished. I will explain. D models, and so this should be explained. D models over K. Now I'll explain. Just the models I explained, which denoted X goes to H and the RAM. So to get this connection. Now, what is the model? It just the model. Now, I'll give definitions for finite dimensional objects because they will be also productive limits. And so let me start. What is the model definition? Now, I've formulated this. So the first definition, E is a finite model of K. So I give definitions only for finite objects, finite dimensional. And so with a finite dimensional vector space over K with a connection Now, if we have, what is omega 1 of K? Omega 1 of K is, in fact, K model of rank 1, the definition. And so if you take var pi, it's convenient generator of the maximal ideal, then omega 1 K is just K times d logarithm of omega. This one form d omega over omega, because it's K is a field of Laurent power series in omega, just the omega. Now, this means that if we can write in such a way, if we have an equivalent form of this connection, X goes to d logarithm of var pi tensor delta var pi of X, where delta of R is a derivation. It's a C linear operator with the following property. If F is an element of K, it is var pi times df with d var pi X plus F is a derivation. And so to define a connection is the same as to define pi. Okay, and so it's a D model of K. Now, if we have second definition, D lattice in E is a lattice, cannot lattice. This means that free module of maximal rank in E, which generates E, such that d var pi of F is preserved by this operator. And so, in fact, one can easily show that it doesn't depend on var pi. One can write it's like connection with logarithmic differential method. And so assume that we have such a dialectic. Now I want to explain what is in distinguished. And also it is important for formulation of the RAM isomorphism theorem. And so if we have such a lattice, then let us consider the quotient of L for the lattice by the submodel generated by the maximal ideal. And so due to this formula, I can see that this operator delta var pi induces an operator delta, which does depend per pi to this, which is called, it's a classical notion, the residue of connection. Residue of the connection delta. Just very elementary. Now let us introduce, so the spectrum of L, and it depends on L. Let me write here L, because it depends on L, it does depend on 1 pi. The spectrum of L is the set of eigenvalues. It's a finite of delta L. The set of, so it's a set of complex numbers. Okay, now the next definition, here, it's third. E is called distinguished if there exists a D lattice A whose spectrum will is a subset of the set of rational numbers. Then one can easily show that for any D lattice L prime, the spectrum of L prime is just a subset of the spectrum of L plus Z. And there exists a unique D lattice, which is denoted in such way, like the ring of integers, such that the spectrum of E node belongs to Q intersected with the unit interval, but unit in the semi-interval from 0 to 1. And so it's a unique, we call it spectrum of E operator. Instead of we just write the residue of the connection data, and E just not the quotient by the submodel generated by the maximum ideal. Okay. Now I'll explain it. So for linearly compact, just projective limits of such objects which preserve all transition homomorphism, preserve all this connection and these properties. Now I want to and so first of all, I can already formulate some property. And so it's a functor which takes analytic space to distinguish the module over K, linearly compact. But first property, it's important that it has relation to the RAM cohomology groups in the usual sense. First, and so like in the classical situation, if X our variety is smooth, it's a usual the RAM cohomology group. And so but here, if X I call rig smooth, this means that it is smooth in the sense of rigid analytic geometry. So all local rings, regular rig smooth, because closed disk is rig smooth, but it is not smooth in the definition. I work with smoothness also requires that there is no boundary. I didn't explain what does it mean boundary. Okay, I'll come to this. And so in any case, if and it's not at all, and either X is confined, it's okay, I recall you, this means that X is isomorphic to such like algebraic variety, quasi-compact special formal schema minus a closed special generic fiber over closed formal subscheme, or X is paracompact. And what I call so paracompact is a usual sense of paracompact. So good means that every point of an analytic space has an affinoid neighborhood. And so I call it such because it's not necessarily. Then these cohomology groups coincide with the usual, and so figure cohomology. First of all, one can, it's reasonable to consider the RAM complex, which is defined for arbitrary x, but only for something smooth. It makes sense. And these are usual, and delta is Gauss-Manin. Connection is Gauss-Manin connection, which can be defined. But one can extend it for arbitrary x, so I do not
X smooth, the model is an open ball.
Yes. What?
An example of X smooth would be an open ball.
No, yes, of course, it's even smooth or restrictive, but closed ball. X smooth is closed ball. Example which is not smooth in the definition I have this, because closed ball.
Closed ball is not X smooth.
No, it's X smooth.
It is.
Because in rigid analytic geometry, closed ball is X smooth, not in the definition I work with. Okay, and so now to continue, now I want to formulate the RAM isomorphism theorem in this non-Archimedean. Let me come back to this. And so I want to associate with E, and so E is a distinguished model. I associate a vector bundle with connection. With connection. First, on the same space, on the same space. And so here is a construction, and so it will be denoted in such a way. It's just we tensor structural sheaf of this space with the residue space. It's the residue space where is the definition. It's here.
I think it's right there.
Yes. It's the residue space. It's called the residue space of E. This means that E naught is the lattice whose spectrum is a subset of this unit interval, and E tidal, the residue space of E, I just didn't write, it's a quotient of this D lattice by the submodel generated by the maximal ideal. It's a C vector space. And so we just tensor product. What is a connection? Now I want to define connection. It's very easy. So first of all, this tensor product, one can easily see it's like omega t. Because E is this tensor product, if you substitute, it's just tensor product of this omega 1 of this space. Now, let me look, what is this space? It is non-canonically isomorphic to C star. It depends isomorphism by multiplication by a complex number. And so it is a vector bundle, free vector bundle of rank 1, and there is a canonical generator, which I denote, and so omega 1, it's D logarithm T. So there is a canonical generator. And so what is a connection? And so F tensor X is an element of the residue space, goes to what is necessary plus F D logarithm T tensor delta of X. It's a connection. And so it's a connection. And so if you start from distinguished demodel, finite distinguished demodel, we constructed vector bundle with connection. And so we can consider the local system of horizontal sections, which is already a local system of vector spaces over Q of the same rank, over C, I'm sorry. Now, if E is not finite, and so I said everything is projective limit, I do not like to consider projective limits of vector bundles. It's better I just for E, which are not finite dimensional, finite, I consider only this local system. And let me come back to here. I'm sorry, so if I denote notation, so if we start from cohomology group, I denote in such a way this local system of linearly compact space, but in fact, if it is a finite dimensional vector space, then even one can consider vector bundle with connection. Okay, and so the Ram isomorphism theory. Isomorphism is that there is a canonical isomorphism of local systems. This local system and this local system. And so if this group is finite dimensional, local system is finite, then even one can write down isomorphism of vector bundles with connection. It's a generalization of the classical Ram isomorphism. And so even I already do not formulate if X comes from algebraic variety over C, then it's really we get. And so first of all, this object is a constant local system which is associated with the Ram homology of this Z algebraic variety. Okay, just let me notice that due to this construction, there is a canonical isomorphism of every fiber of this local system with residue space of E, because it's tensor product, and so it just, there is an isomorphism. Okay, I still have some time, and now I introduce the notion of a mixed Hodge structure over and I didn't yet give the definition of this category. I only said that category embeddable in a boundaryless space, but I will give in a formulation.
Sorry, maybe I missed it. So what is X bar? Is it a compact indication?
Bar? Yeah. It stands for lift to algebraic closure in algebraic geometry. It's just notation.
Okay.
Yes. As a notation, it is not a result of some high direct images of some function. Then it's more complicated. Slightly. It's like a radical homology groups and so on. Again, I give the definition of a finite mixed Hodge structure when everything is finite dimensional, and then I say that linearly compact is projective limits. And so finite distinguished mixed Hodge Q structure is possible. Over K is the following tuple. now where HQ is a quasi-compact, quasi-unipotent local system of Q vector spaces on this space, and W is a finite increasing filtration with the following property. Now I write N WK lies in WK minus 2 minus 1. What it is? What is it? And so it is a local system of this space. It's like C star. And so one can define for any local, such local system, operator N from HQ to HQ minus 1. It's just 1 over 2 of pi I logarithm of sigma I. So if I is the square root of 1, and so one can define, and sigma is corresponding loop, then one can define logarithm or logarithm of unipotent pi. It doesn't matter. And it's 1 over 2 pi I. Because of that, minus 1 here. And so it is a condition. Now, what is E? Is the finite distinguished? No, finite are already distinguished D model. D module over K, over K. And F is a finite decreasing filtration, not on E, but on the residue space of E. Filtration on the residue space, E times residue space of E, the vector space. But what are conditions? Such that, so we know Griffith's transversality relation, but here it's slightly more precise, such that all Fk, and so delta, delta is the operator, it's a finite distinguished D module. There is operator delta on the residue space, and let us consider its additive Jordan decomposition. Semi-simple part plus important part. But the condition on this filtration is that it is preserved by the semi-simple operator delta, and but the important part behaves like it's precisely it's equivalent to Griffith's transversality relation. It's like usually one considers semi-stable. By the way, if we use instead of DS distinguished, semi-stable means that eigenvalues just there is only one eigenvalue 0. Then this condition just automatically satisfied. It's 0 character, but it's precisely okay. Now it's now the third. It's not all. I explain only ingredients, but also there is an isomorphism in this notion, finite distinguished Hodge structure. There is an isomorphism. There is given isomorphism from this to local system, this local system, such that in fact now, or it's a finite, one can also write in such a way, there is an isomorphism, it's equivalent isomorphism of vector bundles. Vector bundles with connection. And so such that now the filtration F induces a filtration on this vector bundle, along by subbundles, just tensor product. Fk is Fk tensor such that if we lift this filtration to this tensor product, we get variation of Hodge structures, variation of mixed Hodge structures, usual classical definition. Okay, now theorem. So it's a definition of. And so it as an object, it's a classical object. It's a variation of mixed Hodge structure on a very simple space on a very special type, and that's all. But it depends on an analytic space miraculously. And so one can for any x. Now I define this category K-analytic space embeddable in a boundaryless space. Define. I didn't yet define part. And so let me remind you that for any K-analytic space, one can define its boundary. There is a notion of a boundary of the boundary of a K-analytic space. Let me just boundary. Now I'll explain. I will not give a definition, but particular cases. Boundary, it is a closed subset. First of all, it is a closed subset. In a sense, analytic spaces like analogs of manifolds with boundaries. An example, if, for example, analytification of algebraic varieties are boundaryless. There is no boundary, is empty. If X is an analytic domain in a boundaryless space, then this boundary is just a topological boundary. For example, closed disk in an affine space, it's boundary. In a fine line, for example, it's a Gauss point. Now, what does it mean that X, it is a subcategory embeddable? This means definition, its definition. X belongs to this subcategory if for any compact analytic domain, any compact analytic domain Z in X is isomorphic to an analytic domain in another K-analytic space, which is boundaryless. For example, if it is just X is an analytic domain in a boundaryless space, just. But in the proof, it's enough to assume this slightly more general. Now, for any, the following tuple, one can provide the following tuple. So I didn't already done. Is a one can define a mixed Hodge structure over K, distinguished mixed Hodge structure, and so on. And this correspondence is functorial in X. It's a full subcategory of the analytic. Now, just a couple of properties. So, what is a V0 subspace? If X is paracompact, then V0 subspace of this local system is a local system. I also a notation, but then I explain what it is. it's a cohomology of the underlying topological space, but it's a local system which takes var pi to the cohomology of the underlying subspace of the following, similar like Eliadic cohomology groups we considered. And so it's a local system which represents cohomology of the underlying space. And so W. Now, if X, first of all, if X comes from an algebraic variety over C, then one gets this a constant local system, this constant, so everything like in Deligne. And now what
is really passing to the algebraic closure of K?
Yes, it's algebraic closure.
Topological space in the sense you use.
Yes. It's underlying topological space of this. It's not rigid analytic space. Now, what are known construction? It's not something which only there is Steenbrink work on limit Hodge structures, and so it generalizes. And even more general case, let me, because I have no time, remind there is a book by Navarra Aznar, where he provided with the mixed Hodge structures certain cohomology of nearby cycles, I call vanishing cycles. And so let me remind that that's finished, because it's curious. It's a particular case, as it turns out. And so what he considered is construction, like in a sense, generalizes classical Hodge theory and Steenbrink book. And so if you have complex analytic from a complex analytic space to C, and we are given a closed analytic subspace which is such that it's a analytification, complex analytification of a proper scheme, with proper Y.
Do you need C or any curve would do?
What?
You have X2C. Do you really need C, or can you take any?
No, in his work, just C, he's considered probably not, but just he considers C. Locally, it's C. Locally, because it's smooth. Like if it is smooth, it's the same like here, because it depends only locally. You see, we have closed analytic subspace, which is an complex analytification of a proper scheme, and assume that we have Z here, which is an open subset, such that Z, in fact, is a complex analytification of an open Zariski open subset in Y, in this one. Then Navarra provided the mixed Hodge structures, the following so cohomology groups of the following complex. I'm sorry, I missed here. So in this situation, one can define SJ7 vanishing cycles complexes, and we consider the cohomology is coefficients in Z. Then these vector spaces are provided, so they're finite dimensional, they're provided with a mixed Hodge structure. So Navarra is now constructed. Now, what is the relation? It's a particular case, and it turns out one can associate with this. If you have such data, one can construct a special formal scheme. Completion of X at Z, which is a special formal scheme. Over the completion of the ring of conversion power series at 0. It's a special, first of all, one do this for Y because it's a proper, and so using some, I was taught, in fact, some theories about algebraic spaces, but then it is an open subscheme in that case. It's a special formal scheme, and so in generic fiber, we can consider it generic fiber. It's an analytic space over a completion of the fraction field. A is a fraction field of this ring of conversion time series. Special formal scheme, and so it's an analytic space over this. And so this proof is just stock of this mixed gauge structure at one point. It includes also, for example, Y can be only 1 point. And here, by the way, X can be generic fiber of such point. So
Questions?
Is there any notion of polarizability? Polarizations?
Probably, yes. I didn't come to this yet. Yes. In fact, I think that I know I use, in fact, I also define homology with compact support, and that's all. And I use some construction to show there is one-color duality and say that weight reflection is multiplicative. I use construction of Fujisawa, Japanese mathematician, and so he considers this organization anyway, as I said. So I didn't.
How do you handle singularity?
Singularity switch, yes. Yes, singularities, just everything started when my former student, Tionkin, proved that there is a functorial desingularization over characteristic 0, not just algebraic varieties, but also formal schemes. So it's a special formal schemes in particular. It's a starting point. So of the whole story.
And then you use the cohomology.
Yes, then I do give a hypercovenant to define complex analytic vanishing cycles. And then it's already that rational cohomology defined in such a way, because for metal cohomology, for finite groups, there is such an isomorphism. Metal cohomology of the generic fiber are precisely cohomology of these sheaf complexes. And so then it's already something non-trivial. I only came to this notion some time ago, no more than 1 year ago, but it's already, it's started. It's very important because it's
Any other questions? All right, no questions. Let's think speak again.